Welcome to qnawire.
Okay, so the reason that acetonitrile appears to be more shielded than the hydrogen in, say, chloromethane or methyl chloride despite the fact that the dipole is larger or much larger in acetonitrile than it is in methyl chloride is due to circulation, right? So I don't know if you've seen this before, but if you have an alkene, recall that it's got p orbitals that are overlapping to make this double bond, and that if you apply a magnetic field that is going, for example, if we point it in the downward direction, let's apply an external field here. Let's say this is B, right? What's going to happen is that the electrons that are in this p orbital actually will start to circulate around the molecule based on the application of that field. And the way in which they do so is that they will go like this, in this direction in particular. Such that outside of the double bond, where the hydrogens are, if the B field is pointed into the page, which I'll put with an X, the B field generated from the circulating electrons is also into the page, whereas it's out of the page in the middle of the bond. The net effect is that these protons are more deshielded than you might expect initially, right? And we see that alkenes, and it's even more pronounced in benzene, are shifted very far downfield. That's true for any hydrogen that's bound to an sp2 hybridized carbon. But when it comes to sp hybridized carbons, as we have in acetonitrile or even just an alkyne, recall that we've got a p orbital that's going up and down, but we've also got one into the page, right? And so what happens is that the circulation effect isn't the same where it goes, in the direction along the protons and against the direction in the bond, right? It actually somewhat opposes the magnetic field, right? It doesn't, right? Like, so in the case of the alkenes, it strengthens the B field because it's in the same direction of the applied B field, the circulation. In the case of alkynes or sp hybridized atoms, I'll sketch it with carbon. With an alkyne, but the same is true if one of the, the same is true for I'll just do it for acetonitrile. We've got carbon, nitrogen, and they've got their triple bond, right? If we apply a B field, say in the downward direction, what we end up with is circulation that looks like this through the p orbitals. All remember that we've got like a p orbital here, and then also into the page and out of the page. Okay, I'm going to remove those for now because it's going to get really messy if I keep drawing them. But that's what we're dealing with here. Okay, what happens is that we get circulation that looks like this. Right. And then recall that we've got our proton here. And the net circulation ends up being one that is like so. Yep, forgive me. Sorry. That's something looked wrong. The net effect is that, there we go. The electrons will rotate in such a way that generates a B field, which will oppose, right? So this is the applied, and this is the induced, right? But the generated B field will oppose the applied B field, right? So this is essentially having a shielding effect. It's not literally shielding it because it's not like, putting electrons around the proton. It's just generating a magnetic field which opposes the applied field. Yeah. So probably sketch something like this to show that the induced field opposes the applied field and explain that it's due to an induced magnetic field. If you want to look up more about this, you could Google like anisotropic induced magnetic fields, anisotropic, let's see, NMR, alkyne, anisotropic induced magnetic fields.